Dr. S. Chandrasekhar received the BE degree in Electrical and Electronics Engineering in 1996 from Jayaraj College of Engineering, Madurai, and ME degree in Power Systems Engineering in 2001 from Coimbatore Institute of Technology, Coimbatore. He has received the PhD degree from IIT Madras in 2005 in the area of high voltage technology. He was a postdoctoral research fellow at the University of Bologna, Italy from 2005 to 2006, where he worked on high voltage insulation systems and smart grid technology. He is presently working as a Dean R&D at Sona College of Technology, Salem. He is the head of the Sona PET, Sona Electric Power Engineering Research and Testing Center, R&D Center at Sona College of Technology. He has received the prestigious awards such as Career Award for Young Teachers from AICT New Delhi in 2008, UGC Research Award from UGC New Delhi in 2015, Best Faculty Award from NGA Coimbatore during 2011, Best Principal Performance Award from Global Achievers Foundation New Delhi during 2012. He has also acted as a Board of Studies member of Anna University Chennai and Jayaraj Polytechnic College. He has also so far successfully completed several funded research projects sponsored by various government organizations and industries to the tune of ₹4 crores. He has also filed 4 patents in the area of nanoelectricals and high voltage technology. His research interests include development of advanced dielectric materials for high voltage power transmission systems and development of condition monitoring systems of high voltage power apparatus. He has also involved in the consultancy projects such as development of regulated power converters for submersible ROV applications and electric drives for deep sea mining applications. 15 scholars completed PhD degree under his guidance, and he is presently guiding 6 PhD students under Anna University Chennai, and he has published more than 200 research papers in various international journals and conferences, which also include 10 papers in IEEE transactions and 35 papers in SE indexed journals. Dr. Chandrasekhar sir, who is an expert in all aspects, has accepted our invitation in spite of his busy schedule to enlighten us with his knowledge and experience. So with these few words, I would like to hand over this session to the resource person. Sir, please, sir.
Yes. Thank you, Dr. Balakrishnan. First of all, I would like to thank the organizing committee and the Gnanamani College, management of Gnanamani College of Technology for giving me an opportunity to share some of my views on sensors which are useful for high voltage systems. Thank you, sir. So shall I start the presentation?
Yes, sir. You can go ahead.
Is it visible, sir?
Sir, visible, sir.
Okay. So the committee selected a very good topic, sensors. This is really a very useful topic, as all of you know that today's world is even fully controlled by sensors. I can tell that everyone is even controlled. A simple example is the CCTV camera, what we have installed everywhere. So the movement of even each and every individual person is monitored, and it's like a very good example of a sensor. And also, as you know, the sensors, simple sensors like temperature sensors, pressure sensors, humidity sensor are used everywhere. Without sensors, there is no life. From my room, I can control the washing machine or fridge in my house, and even in the case of agriculture, people are trying to control their pumps and other devices which is far away from their home, and they are simply controlling all those things through sensors. Initially, the sensors are developed for monitoring purpose, whereas in recent times it is also fully used for control. So both control and monitoring is possible through the sensor technology. And as all of you know, even the famous the initiatives taken by Tesla and Google for developing autonomous vehicles, driverless car or self-driving car. So all these things are very good examples for sensor technology. A car without any driver is possible only because of the various types of sensors. Hundreds of sensors are working at the same time, and they're controlling the direction, speed, and position. Everything is controlled through sensors. So such a technological advancements are possible in this field of area actually. And recently also, the coronavirus has created a lot of impact, and people are also talking about electronic nose. They are also doing research on electronic nose, which is capable of sensing whether a person is affected by COVID or not. So in such a way, the technology is advancing, and everywhere sensors are used. And the latest one is also the wearable technologies. So initially people started wearable devices, and in a simple hand watch, it is possible to monitor your body temperature and everything. And also nowadays even wearable textiles are also coming forward, whereas the shirt or pant what we are wearing, in that they are including all those sensors, and it's regularly used to monitor your ECG and pressure and temperature. Everything is monitored. So in such a way, the sensor technology has really got a very good development in the last 4 or 5 years, and now we are all benefited out of it actually. In this pandemic situation also, sitting in our room and sitting in our house, we are able to do all the works and everything. It's because of the developments in communication technology, networking technology, and the latest in advancements in IoT, artificial intelligence, and embedded systems. So all these things combined together along with the sensor technology, they are providing a successful life in such a pandemic situation. So that's why I told this topic, the sensor technology taken by Gnanamani College of Technology is really a useful topic. I hope all of you might have really enjoyed these 4 days of session. And the Internet of Things, as you know, instead of Internet of Things, nowadays people are also telling Internet of everything. So Internet of everything means anything is possible to control from anywhere in the world. So that's what the concept of Internet of everything has come. And even the industrial IoT also is becoming popular. So we are able to monitor all devices. Particularly today, I am going to focus on high voltage systems. As all of you know, what is high voltage, and even some people might have studied high voltage engineering during their BE degree course. And most of the people, even including myself, at that time when we studied this high voltage engineering, we thought it is a fully theoretical subject, and it's a boring subject, and we don't concentrate much on the subject. Whereas really, in the case of industrial applications and also real-time works and job-oriented course means, then it's a high voltage engineering is really a useful topic. And in very few institutes in India, they are offering this course, high voltage engineering. because of the lab facilities what is required, because we need to invest crores of money in establishing the high voltage facilities in the campus. So that's why in very few institutes only this course is available, whereas regarding job opportunities, if you see, then there are many opportunities, particularly if you see many companies like GE, Alstom, L&T, Arriva, and Crampton Greaves, and then even CPRI. There are so many big giants are there in high voltage technology. They are all working in high voltage products, and therefore they are also in need of people with good design knowledge and good testing knowledge and service knowledge. So they are looking for people with good expertise in high voltage technology. Really, as the communication technology and the sensor technology is growing fast, they are also looking people who have some fundamental knowledge in high voltage sensors and high voltage measurements and testing. So they are always looking for people, whereas since most of our students are always focusing towards software jobs, they are really, I think they are missing the great opportunities what is existing in this power sector. So this high voltage, that's why I as I get as I have a lot of experience in high voltage side, and for the past 20 years I am working in high voltage engineering. So I thought to give a small awareness about this high voltage systems and sensors what is used in the today's world. Okay, so high voltage means most of the people, they will think that even this the commercially available power sources, what is available in our household appliances like 230 volt AC, or in some countries they are using 110 volt AC. It is not a high voltage. Really, it is not a high voltage. It's a in our terms, it is really a low voltage. But people who are all dealing with the electronics, particularly these embedded systems and IoT, and all those people, they tell the low voltage means that 0 to 5 volt and 0 to 10 milliamps, what they use regularly for their electronic products and processors. So this is what they think as low voltage, and 230 volt and 110 volt AC or DC, whatever may be, it is they are thinking as high voltage. But really, it's not so. So the real high voltage is something in kilovolts. So that's what is called high voltage. For low voltage side, the technology is fully developed. For example, if you want to measure any voltage, for example, in our house, if you want to measure the 230 volt AC or 110 volt AC, whatever may be, we are having so many devices, for sensors are available for that. The current sensors are available, voltage sensors are available, and very compact devices are also available. So you can easily measure or monitor the voltage and current and everything. That's why even the digital meters are also everywhere now installed, and all those things are having the smart low voltage sensors, that particularly current sensors and voltage sensors. These sensors these sensors are dealing with very low voltage. For example, voltage means it is around 0 to 5 volts. Normally the voltage transducer is handling, whereas in the case of current sensor, it is normally 1 amps or 5 amps mostly. So any CT or any PT, current transformer or potential transformer, what is used in regular commercial applications is in this range of 1 ampere to 5 ampere, and maximum 0 to 5 volts potential transformers. But really, in the case of high voltage systems, it is not so. So as I already told, we are dealing with kilovolts. In high voltage itself, there are so many classifications. For example, medium voltage, then high voltage, then extra high voltage, then ultra high voltage. Like that, in high voltage system itself, there are 4 different classifications. In medium voltage, it means that it is dealing with 11 kilovolt to 33 kilovolt. This 11 kilovolt to 33 kilovolt is not what we normally use in distribution systems. In power systems, we have two majorly two components. One is transmission side, another one is the distribution side. In distribution side, we are dealing with 11 kilovolt to 33 kilovolt. That is normally called as medium voltage. Whereas a high voltage means it is above 33 kilovolt. That is from 110 kilovolt to 440 kilovolt. So that is most of the transmission lines installed in our country are coming under this category, 110 kilovolt to 440 kilovolt. Whereas the extra high voltage means above 440 kilovolt. So above 440 kilovolt means the next line is 765 kilovolt. So that is called extra high voltage. Whereas ultra high voltage is the latest technology what Indian government is trying to establish, that is about 1200 kilovolt. So there are 4 different categories. Up to 33 kilovolt is medium voltage, and 110 kilovolt to 440 kilovolt is high voltage, whereas above 440 kilovolt to up to 765 kilovolt is called extra high voltage, and ultra high voltage is above 1000 kilovolt. This 1200 kilovolt is normally used in practice. Okay, so similarly in the case of DC lines, DC power transmission system is also, in high voltage, a separate high voltage DC lines are also there. In DC lines, we have reached up to 400 kilovolt, and then recently we have also reached up to 800 kilovolt. So like this, the high voltage means it's all in kilovolt range. So now I am going to.
Excuse me, sir, your slides aren't moving, sir.
Yeah. Now is it okay?
Yes, sir.
Yes,
Are you
yes.
on the second slide? Slide number 2.
Yes.
Volume sorry.
Okay. Am I audible now?
Yes.
Yes, sir, it's audible, sir.
Okay. So, what today I am going to deal with is a common term, high voltage, which means above 11 kilovolt to up to 1100 kilovolt, whatever is coming in that range, we are calling it as a high voltage. Okay. So the developing the technology for measuring these high voltages and high currents, it's really a tough, it's a challenging task actually. So in India, we have reached 1200 kilovolt AC transmission systems, and in DC we have reached up to 800 kilovolt transmission systems. So as you know, once we are generating power in the power stations, the thermal stations, or any nuclear station, whatever may be, the generated voltage is in the range of 11 kilovolt to 33 kilovolt maximum. Most of the places we are generating the voltages at 22 kilovolt. So now we are transmitting this power through transmission lines and distribution lines. So everywhere for transmission at very high voltages, we are going to use transformers for step-up operation, and also at the consumer side or industrial side, we are again going to step down the voltage. So these things, So everywhere we are using transformers, and in cities we are using cables, underground cables. And most of the places we are using 22 kilovolt cables for transmitting power. Even in Europe and other countries, the people are also using 110 kilovolt or 220 kilovolt cables, underground cables. So like that, the power transmission and distribution system consists of mainly 2 components. One is the transformer, and another one is cable. So in such a case, I don't know whether you people know or not, a high voltage transformer, you cannot imagine, it will occupy almost one master bedroom size the space. Okay, a 16 cross 16 like that, a very huge space is required for installing a transformer. So such a huge space means you can imagine what is the cost of that transformer. The cost of the transformer is in crores, 5 crores, 6 crores, a single transformer. So if you think 1200 kilovolt, then in order to step up the voltage up to 1200 kilovolt means, then the size of the transformer, you can imagine how big it is. And when we are going for high voltages, then naturally we need to concentrate more on insulation systems. When we are dealing with current, then we need to concentrate more on the conductor. Whereas when we are concentrating more on voltage, then we need to discuss about insulator. Because once the insulation fails, then naturally the total system will burst. You can you might have noted in many news that the transformer burst, and there are so many such accidents and shutdowns happened. So it's all due to the failure of insulation what is present in that particular high voltage component. So that's why whenever we are dealing with the high voltages, then naturally we need to discuss about the insulation what is used in the in such a systems. Okay. So as you know, mostly what are all the insulations are mostly used. There are only three basic fields are there: solid insulation and liquid insulation and gas insulation. And why I am talking all about these things is that we are going to deal with the high voltage sensors. High voltage sensors to understand the problems or the health condition of the expensive components like transformers and cables. So for that we need to know some fundamentals. What are all the things we are going to monitor really in a transformer? So that's why I am telling some introduction about these things. Okay, so such a big huge devices like transformers or even in cables, we are using all these types of insulations: solid insulation and liquid insulation and gas insulation. Even in Chennai, there is a completely gas insulated substation is available. In Mylapore, there is a completely gas insulated substation. SF6 gas insulated substation is available. This is mainly by choosing the dielectric strength of the medium. Okay, so the gas insulated system has a very good dielectric strength. That is very good insulation properties than the solid and liquid. And in liquid is mostly preferred in transformers. Why? Because it has that self-restoring capabilities, and also we can easily replace the liquid insulation. So in the case of transformer, even you know what is transformer? No, there is one primary winding and one secondary winding is there. And in between windings also we are using press board insulation, a paper or a solid insulation. So like that, even inside the transformer, we have a solid insulation and also liquid insulation. Both are there. So hybrid insulation system is followed in such a big instruments. Okay. So in such a cases, how to measure this high voltage? As all of you know, we have standard current transducers or voltage sensors or current sensors which are available at 0 to 5 volt and which has maximum input capacity of 0 to 230 volt. If you see the voltage transducers developed by LEM, a famous company, then the maximum input voltage what we can give is up to 500 volts we can give. It will convert that 500 volts into 5 volts. Even in current rating also, if you see maximum input current you can give up to 35 amps or 50 amperes, that will be converted to 0 to 1 amps or in milliamperes. So which is that low voltage which is useful for your embedded processors and other things, because in most of the microcontrollers or processors you cannot exceed beyond 5 volt. So that's why all these sensors and output are calibrated to 5 volt or the current rating is in 0 to 10 milliamperes. Okay, so in such a case, how to measure this high voltage or high current? So the very common technique is that in order to measure the high voltage, people will be using simple divider circuits. This simple circuit theory is mostly followed in many places. If you use a simple resistive divider or a simple capacitive divider, then you can easily measure the high voltage. Okay, and if you are using a combination of resistive and capacitive divider, then we can easily measure the high voltages. And also in for measuring currents, we can go for current transformers with low secondary rating, so that you can easily measure the currents. Okay, But these are all very conventional measuring techniques, and these instruments mostly deal with low frequency. For example, they can measure only up to 50 hertz to some maximum 500 hertz. That is, you can measure only some up to fifth harmonics or sixth harmonic, like that only. So you know what is harmonic frequencies. So most of these instruments, current transformers and potential transformers, they are all conventional types, and they deal with 50 hertz to some up to some 10th harmonic order. So with these devices, we can only able to see what is the current flowing and what is the voltage available in the device. Okay, so whereas but we need to understand actually if there is any fault inside the transformer, or if there is any fault in the cable, underground cable, then what are all the sensor technology available to measure those types of faults. So that's what we are going to focus in this particular session. Okay, so I will just give a brief introduction of a transformer and cable, what is used in high voltage side. Okay, so you know, this is as I already told, there are so many transformers in distribution side, and existing in service for more than 20-25 years, and still running, and is still running under overloaded condition. In many places, the transformers are the fault is happening because of the overloaded condition, because it is overheated. So naturally, the insulation inside the transformer, oil insulation, is degraded, and so it results in short circuit, and therefore it bursts, and there are so many issues are happening in transformers. Okay. This is a picture of a simple 11 kilovolt to 33 kilovolt distribution transformer. And even in transmission line transformers, as I already told, 110 kilovolt to 765, and even India has now developed 1200 kilovolt transformer, which is, I think, jointly developed by CPRI and Bell and Arriva, some 2-3 big giants. They jointly developed that very high, ultra high voltage transformer, so 1200 kilovolt. Okay, so most of the causes for power transformer failure, if you see, some of them are natural. For example, the failure due to lightning. So lightning is 25%, so which we cannot avoid actually, because it's a natural phenomena, and once lightning strikes, then immediately the entire thing bursts, and we cannot avoid such a problem. Whereas the next major one is the failure due to insulation. So it is almost 15%. So 15% means there are thousands and thousands of transformers are located in all over the country, and if you consider the 15% of the transformers fails due to this insulation, then we need to give much more importance and focus on the insulation system. That's why I told whenever we are dealing with the high voltage side, then naturally we need to concentrate more on the insulation what is used. Okay. So as you know, there are so many stresses acting on a transformer in a day-to-day life. Among that, the mechanical stress and thermal stress and dielectric stress, there are so many stresses are there. And in mechanical stress, it is mainly due to the overcurrent and fault currents by short circuits. And thermal stress is due to overheating of the and local hot spots. And the dielectric stress is mainly due to the over voltages, switching over voltage and the transient over voltage and the lightning impulse over voltage are due to any resonance within the winding. So all these stresses are acting on the transformer, and it slowly degrades the insulation what is used inside the transformer. So another important equipment in high voltage system is underground cables. Okay, so these high voltage or medium voltage underground cable, you can see the big picture in the side. It is the underground cable what is installed in Europe, okay, in Italy, and then so they have a well planned structure built for laying of these underground cables. Okay, even in our country also, people are using 22 kV underground cables in cities, most of the cities, and it is just like that. They are digging and they are just some they are keeping inside without any protection. Whereas you can see these pictures how well it is protected. Each face of this cable is how well it is protected, and even it is very tough to any moisture or any contamination to enter inside the insulation of this cable. Okay, so in such a way they are maintaining because it's very costly. As you know, if there is any fault in underground cable, attending that fault is very difficult because the cable runs for kilometers. Okay, several kilometers. So normally it's from 2 kilometers to 5 kilometers, like that the cables are running. And in such a cases, if there is any fault in any one place, then it is very difficult to find out that particular fault and digging that particular exactly that portion of the cable and removing that particular portion of the cable and replacing it. All these things are very tough in the case of underground cable systems. So that's why in Europe countries and in US, they are making very big channels like this, and they are properly installing all these underground cables. And even at many places, intermediate places, they are giving monitoring stations so that if there is any fault, they can easily monitor in the intermediate positions. So like that, they are installing these cables in foreign countries. Okay. So in the cable also, it is full of solid insulation. It is made up of ethylene propylene rubber insulation or XLPE insulation. So the cable, as you know, the structure of the cable, the center of the cable is a core, and then there will be an insulation, and again a metallic sheath for earthing it is provided, and again one more insulation will be there. So this diagram clearly shows there are two insulators, but both of them are having the same type of insulation. For example, if they use XLPE, means cross-linked polyethylene material. So it means then at both places they will use the same XLPE, and a metallic sheath will be provided. Aluminum or copper metallic sheath will be provided. Okay, so this is the common structure of the cable. So in the case of cable also, we can see there are so many stresses. What we already discussed about transformers, the same type of stresses, electrical stresses, mechanical stresses, and thermal stresses, and environmental stresses. Here environmental stresses means the humidity or moisture content in the soil, and what can ingress into the material, and it may degrade the quality of the solid insulation slowly. And like that, mechanical stresses normally happens during bending, and electrical stresses, as you know, due to the over voltages, switching over voltage and lightning impulse over voltage. So electrical stresses are happening. So these are all the various stresses normally experienced by underground cables. So as you know, in the case of high voltage systems, the 70% of the transformer or cable failure is due to the insulation. So the reason for the weakness in the insulation is because of the presence of impurities, moisture, and overheating, and there are many stresses what we already discussed. And these reasons, it creates partial discharges or leakage current inside the insulation, and it leads to aging and deterioration of the system. So you can see that an insulating medium with 3% of moisture content will age 30 times faster than 1% moisture. So it's really how fast it will age when the percentage of moisture it slightly increases. So you can see how environment plays a major role in the degradation of this insulation of the systems. Okay. So now, as I already told, we are going to deal with the various sensors, how to monitor the performance of transformers and cables. Okay, so mostly in conventional systems, people are using these parameters, the dielectric breakdown strength, or tan delta, or relative permittivity, or insulation resistance. These are all the common parameters which are measured regularly, and they will judge the aging process or the performance of the insulation system in transformers and cables. But these are all laboratory based procedures. So as now we are moving with advanced communication technologies, now everyone wants to monitor each and every item and every parameter through IoT based concepts and through embedded systems. And therefore we want to even measure through our mobile apps and from any place. So also we want to control those things from anywhere in the world. So in such a cases, monitoring these regular parameters in the laboratory is very tough actually. So that's why today the latest technology is the measurement of partial discharges and the measurement of leakage current signals and partial discharge signals in the case of transformers and cables. So it's a very hot topic of research, and many people are working on this, and they are giving many solutions for this, how to measure these partial discharges and leakage current. So now I am going to discuss about the partial discharges, what is happening in this case of transformers and cables, and how to measure these PDs, and what are all the sensors used for measuring these PDs in occurring in high voltage systems. So partial discharge is nothing but a localized discharge, what is happening in an insulation. Okay, so in the left side you can see the picture where an electrical avalanche or PD, what is occurring inside an insulation, it is shown. One top electrode is applied with high voltage and bottom is grounded, and therefore you can see this is the insulation PD occurring inside the insulation. It is mainly because of any delamination or any presence of void or any bad connection. So all these things are the major causes for the PD, what is occurring inside the insulation. Okay, there are different types of PDs. Okay, one is we can classify it as internal partial discharge and corona partial discharge or surface partial discharge. You can easily visualize in a transformer, a big size transformer, which is fully filled with oil. Okay, so transformer oil. So in that transformer oil only the windings are immersed, primary windings and secondary windings are immersed. So it is applied with the high voltage. Okay, so what is happening? So when there is an oil, then if it is getting overheated due to increase in temperature due to overloading, so what will happen? It will create some bubbles. Okay, inside the oil, the bubbles will be created. So the bubbles are nothing but cavity or voids. Okay, so there it will easily break down, because since the voltage is very high, the bubble is simply filled with air. Okay, so bubble is simply filled with air. So the air has a very low dielectric strength when compared with the oil, and therefore the air will simply break down. So therefore it will create a discharge inside the oil. So like that, if there are so many bubbles or so many cavities forming inside the oil, then what will happen? Then it will lead to so many discharges at different places. So this is simply an arcing. A partial discharge is simply a small arc, what is happening inside the insulation. So if this arc continues for a long time, then it will slowly bridge down, and then what will happen? It will short circuit the high voltage point and the ground point. So then it will lead to a complete short circuit, and therefore then only the sudden bursting of the transformer or the failure of the transformer, shutdown of the transformer happens. Okay, so the presence of these partial discharges inside the insulation system, in particularly in transformers and cables, leads to a very big failure. Therefore, monitoring these partial discharges in the initial stage itself, really it will give a very good preventive maintenance solution for such a costly equipment. A transformer of 5 crores or 6 crores installed, and suddenly after 6 months or 1 year, due to bad insulation system inside it, if it fails suddenly, and yes, fraction of seconds, that 6 crores will have gone. So, in order to avoid such a failure of such a expensive systems, nowadays people are using advanced high voltage sensors. Okay, so that's what dealing with partial discharge sensors. Okay. So this is a typical partial discharge signal, what is happening inside the transformer. And this partial discharge signal has a rise time in the range of nanoseconds, or microseconds, and the tail time also in the range of microseconds, and the peak value will be in some volts, and then its frequency will be in megahertz. Okay, so once a partial discharge occurs inside the transformer insulation, then it will give a signal like this. Okay, so this signal will travel along the insulation, and if we keep any sensor to measure these signals, then naturally we will be able to understand what is happening inside the transformer or cable. Okay, so it has the specific characteristics like this. All are in microseconds and nanoseconds, and its frequency is in megahertz. Therefore, we cannot use a conventional sensor, what we dealt initially, the current transformer or potential transformer, which is operating at low frequencies, 50 hertz to 500 kilohertz, 500 hertz. So those things are all we cannot use for measuring or sensing these types of high frequency signals. Okay, so these signals are I have mentioned 500 kilohertz to 50 megahertz frequency. So it is occurring in such a very high frequency. Therefore, we need to find out a proper sensors for measuring these signals. For example, you can see some of the case studies here. A 33 MVA transformer, high voltage transformer. There is a fault. So when we inspected inside, then we can find out the overheated joints. So in the joints, continuous arcing happened, and therefore you can see that complete blackish portion. It is because of continuous arcing or partial discharge occurring in those portions due to the overheated joints. This is also in another case study, the same 33 MVA transformer. So in it has 3 phases, and in phase B, we have found out that there is an L plate and in the tap changer support and OLTC drum. So in between that, there is a continuous arcing happened. So that blackish portion, it clearly shows the continuous arcing happened. If this arcing continues for a long duration, and if someone is not attending this problem, means then what will happen after a long time, then it will lead to one day, it will lead to complete failure of the system. Okay, so that's why like the sensors how we are using for our household applications, similarly for high voltage systems also, these costly equipments, and now everywhere people are using sensor technology, and they are installing sensors to continuously monitor these types of preventive maintenance activities. Monitoring the regular current and voltage at low frequency, regular frequency, there is no use in that actually. So monitoring such a type of very high frequency signals, particularly these fault signals, and then understanding what is happening inside it, and then exactly finding out the source of this fault, and classifying those faults, and finding out the data mining approaches. So all these things are the really hard research topic. So this is similarly a partial discharge occurring inside the cable. Okay, so you can see the picture in the cable insulation. Slowly the arcing developed, and it is now growing, and it is moving towards the ground electrode, and you can see it is forming like a tree. So that's why it is called electrical tree in a cable. So it is mainly due to the partial discharge activities in the cable. So while manufacturing that time, if there is some void or some cavity formed inside that insulation, and then it will slowly leads to the partial discharges, and finally one day that particular portion of the cable will burst, or short circuit will happen. Okay, so these are all the major problems in cables and partial transformers. So in order to, now we are coming into the sensors. Okay, the partial discharge sensors, what are all commonly used for this high voltage measurements. Now I hope you understand what is high voltage, and also what is the importance for monitoring the insulation systems in high voltage. And then if there is any failure in insulation system of this high voltage, then it will lead to a major economical loss and also complete shutdown of power. Therefore, as a preventive maintenance work. Nowadays, all electrical utilities are giving much preference for understanding the technologies for high voltage sensors. Okay, so these are all the high voltage sensors available. HFCT and LFCT. These two sensors are inductive type sensors. HFCT means high frequency current transformer, and LFCT means low frequency current transformer. And then based on the piezoelectric principle, the acoustic sensors are also developed. And then UHF sensors, ultra high frequency sensors are also there. And even in TEV sensors also there, transient earth voltage sensors are also there. Okay, so there are so many sensors like this developed for understanding the discharges or leakage currents happening in high voltage systems. So we will see one by one. Okay, you know the basic principle of current measurement. Okay, the current sensing is basically simple Ohm's law is followed, whereas direct sensing and indirect sensing, two techniques are commonly followed in current measurement. In laboratory level, we are dealing with this direct sensing, where if you want to measure current in any portion, we will simply insert a resistor and we will find out the voltage drop, and then we will tell how much current is flowing in that particular circuit. Okay, so this is a very simple direct principle, whereas the indirect sensing is nothing but it is based on that Faraday's law of electromagnetic induction, where if there is any current flows, then it creates a magnetic field, and therefore using that magnetic field we will be able to generate a voltage, and according to Lenz's law, and therefore that voltage will tell what is the current flowing in the main winding. Okay, so this is indirect sensing based on the magnetic field principle. The main advantage of this magnetic type field is that complete isolation is possible, because now everywhere we are talking about isolation between the high voltage side and the low voltage side. Since the low voltage electronics is also a very costly one, at the same time high voltage side is also a costly one. If during measurement, if high voltage ground and low voltage ground are interconnected, and if there is any problem, then both systems will get collapsed. Therefore, in order to avoid those things, everywhere people are talking about isolation between high voltage side and low voltage side. So this magnetic field based indirect sensing, it will give a complete isolation between high voltage and low voltage side. So these are all the high frequency current transformers. So this is a very reliable method for measuring high frequency PD pulses. So there are also split core type is available, and clamp type is also available. And in any ground lead of the transformers or cables, if you connect this high voltage HFCT sensor, then you can easily measure the high frequency signals. Okay, so that is possible through this HFCT sensors. So this is a simple measuring concept of the HFCT sensors, the high frequency current transformer sensors in the case of online PD measurement. Okay, so through the ground line, we need to connect this HFCT sensor, and through the BNC cable, we can connect it with any measuring instrument. Even a simple CRO you can measure, or if you want to go for any advanced PD systems, then we need to place a permanent data capturing system, and then that should be interfaced with the cloud, and then you can process it remotely. So in such a way, we can connect easily this HFCT sensor. And these sensors are mainly used for measuring only high frequency signals, and we cannot measure a conventional 50 Hertz current through this sensor. Okay, so it's a special sensor made for measuring these types of transient signals or high frequency signals. Okay, and this is the frequency response of this HFCT sensor. So the normal bandwidth is 0.5 megahertz to 50 megahertz. You can see the picture. The major advantage of this HFCT sensors is that it can measure the PD signal or any high frequency transient signals occurring in cables at a distance of 1 kilometer. Okay, so up to 1 kilometer also, these type of sensors can easily measure what is happening in the transformer or cable. And this is a typical photograph which tells the HFCT sensor connected in a power cable. Okay, so the main cable is there, the black portion, whereas the ground lead is a yellow color portion. In the ground lead, if you connect, then any partial discharge what is occurring, any leakage current or partial discharge what is occurring in the cable, that will flow through that metallic sheath and which is grounded. So we can easily get those signals through this HFCT sensor, and we can easily identify what is happening inside. Okay, if the level of the partial discharge or the leakage current if it exceeds the threshold limit, then we can immediately do the preventive maintenance work. So this is the sensor, HFCT sensor installation in the terminals. Okay, the normally the ground it is connected in the ground connection, and the top portion is the high voltage bushing, and this HFCT sensor and the LRCT sensor both are connected in the ground leads. So through that it will be connected to PD measuring system, and the further it will be connected with the communicated with substation operator. So this is the type of connection, sensor connection at joints. Okay, so if it is a 3-core cable, 3-phase cable, then for example, if the red phase is under test, then we are connecting that HFCT sensor in the red phase, and both the blue and green phase are short circuited. So we can easily measure what is happening in the red phase. Okay, so while measuring one phase, then other 2 phases should be short circuited in order to avoid false readings. Okay, so these are all some of the real pictures in the termination and in joints. So how these sensors are connected. So before starting the measurement through this HFCT sensor, then we need to calibrate this sensor. Okay, whether we are really measuring a PD signal or not. So that one we need to understand. So before that, I would like to show you one small video of Is it visible?
Yes, sir.
Okay. So this is the high frequency current transformer sensor, which is connected in the ground lead of the terminal, and then they are measuring the leakage current or partial discharge, what is happening inside, and this is the partial discharge detector. Okay. So like this, it is a very simple connection. It's a split core type HFCT, therefore you can easily connect in any ground lead. Okay. So this is a very advanced sensor which will operate in 50 megahertz bandwidth. So now my presentation is visible or not? Is it visible, sir? Okay. Now is it visible? Slide.
No, sir. Slide is not a
Yes, sir. Slide visible, sir.
Okay. So is it visible now? Yes. Okay. Yeah. So now, as I already told, the calibration of these sensors, these high frequency current transformer sensors, for particularly for high voltage applications, is very, very important. and whether we are really measuring partial discharge or any other signal, that's really a big challenging task. Why I am telling this is, this sensor, this HFCT sensor, it will capture all the signals which are available in that surrounding area. It is coming.
Sir, excuse me, sir, your slide is not visible, sir.
Okay, slide is not visible.
Still in the video section, sir. So you can just give the stop presentation and begin your presentation again with the full screen.
Yeah, is it visible now?
Yes, sir, now it's visible, sir.
Okay, okay. Yes. So now the real challenge for a test engineer or the persons going for monitoring these types of activities, no, it is to understand whether we are really measuring the PD signal or leakage current signal, what is happening inside the equipment, or whether we are measuring some unknown signals from outside. So it's very, very tough actually. Why I am telling this is because these sensors are all working in very high frequency. For example, this one is working at a central bandwidth of 50 megahertz. So 50 megahertz means it will capture the signal from any 5 megahertz to 100 megahertz, any signal it will capture. Okay, so before starting the experiment or before starting the measurement, what we need to do is that we need to have a calibrator. So that calibrator is shown in this picture. Okay, so it will inject the known signals, PD signals of a particular frequency. We can set what is the frequency of the signal we want to inject, and then using this calibrator, we need to inject that particular signal into the test equipment. For example, if it's a cable or bushing, then we need to inject that particular things to this bushing, and then we need to measure the PD signal through our sensor. And if our sensor is able to capture exactly that magnitude and the frequency of those PD signals what we injected, then it is working perfectly correct. So such a calibration procedure should be followed before starting the measurement. So it is very, very important. Why I am telling is that it's actually when I was there as a postdoctoral research fellow at Italy, and we used to go for this real-time monitoring systems and in tie-up with industry. And one day when we went for this underground cable monitoring, that time actually the practice is that the cable will be of several kilometers. Therefore, we need to monitor the cable properties, or particularly the PD activities at different terminations, at different junctions. Okay, so we need to start early in the morning the procedure, so that before evening or 7 o'clock or 8 o'clock we can finish the work, entire work. So we used to start the work, and in the morning we started measuring PD, and we got continuous PD in one particular junction. One particular junction, when we measured, we are continuously getting the PD activities. But it is a new cable, the new fresh cable installed in that system, and we cannot expect any problem or dielectric problem or leakage current or PD in a fresh cable. So we are really confused. What is this? It is showing like this, and then after some time, when we moved away to other terminations, then there was no problem, no signal at all. Completely lost, no signal is there. So at the evening again, when we measured at one particular termination, we are getting the same type of signals. Okay, so we are really confused. What is this? Whether we are really measuring PD or which one, like that? Because it's a new place to us. We don't know about that place, and then we stayed one more day there, and when we inquired about our problem with the concerned representatives of that particular place, and then they told that there is a small radio station is available in another 1 or 2 kilometers. That radio station is running in these times. Morning time this 1 hour, and then evening time in this 1 hour, like that it will be running. So maybe you can cross check like that, they told. Then only we came to know that, so we didn't measure PD signal, we really measured the radio frequency signal of that particular frequency in our PD system. So that's why that particular timing we got the continuously the signals, and those signals are all not PD signals. So like that, so the measuring PD in very high frequency, not only in PD, any high frequency signal measurement is really very tough, because there are so many radio frequency interferences and then noises occurring in and around the environment, and therefore even a cell phone signal, while performing these measurements, even sometimes even if you are getting any cell phone call or any cell phone signal, then you will get some disturbance or noise. You can easily visualize in the computer. So like that, what is really a PD and what is noise and what is interference and radio frequency interference or any other noise, we need to clarify those things, and then that expertise should be developed from the test engineers. Okay, so that's why the sensitivity check or calibration of the PD sensor, and then understanding what is really whether it is really a fault inside the transformer or cable, or it is something some unwanted noises coming out from outside. We need to distinguish or differentiate those things. So next one is the low frequency current transformer. This is also, as I already told, it operates in 50 Hz to 1 kHz low frequency, but it can measure high currents, but at the same time the frequency level is very low. So it is normally used for synchronization signal, because mostly in the case of high voltage systems, they would like to measure any high frequency signal in synchronization with our power frequency, and therefore in order to synchronize the power frequency and the high frequency signals, they will use to capture these low frequency current transformers. So this is mainly used for synchronization purpose. So the next technology is acoustic sensors. Okay, as you know, acoustic sensors, it's mainly based on piezoelectric principle. So this is a typical acoustic sensor. The picture shows a typical acoustic sensor. And its basic principle is there, the piezoelectric substrate, and then therefore it will convert the electrical signal to mechanical waveform, and then again it will convert back into electrical signal. Okay, so how these acoustic sensors are used for high voltage transformers. Okay, so why we are going for acoustic sensors in high voltage transformers? Why? Because as I already told, the transformer is of very large size. Therefore, it is completely filled with oil, and therefore, if there is any fault in a particular place inside the tank, then it is very difficult to locate that fault. Using a high frequency current transformer, what we already discussed, using that sensor, if you get a PD signal, then we can tell them that some PD activity or some leakage current is happening inside the transformer. Whereas, in order to accurately locate where is the fault or in which winding, there are so many primary and secondary windings are there, consisting of so many turns. So, in which portion of the winding the fault is occurring. So, like that, if you want to pinpoint that exactly the fault location, then we need to go for such acoustic based sensors. Yeah, I will also show you one small video of acoustic sensors.
NDB Technologies presents the AE-150 Partial Discharge Localization System for Oil and Power Transformers. One of the most expensive elements in a power grid are substation power transformers. They typically are subject of routine maintenance testing, whether it be online or offline. DGA, or dissolved gas analysis, is part of this test. The results can correlate to potential problems in the transformer, including partial discharge. and that is when the AE150 comes into action. Partial discharge will emit very high-frequency electromagnetic and acoustic pressure waves inside the power transformer. The AE150 relies on 4 acoustic emission sensors and an electric PD sensor input to locate the source of partial discharge. The result is a 3-dimensional graph where vectors and pinpoint data provide X, Y, Z coordinates inside the transformer. Using the AE150 results, the operator will need to consult internal schematics or conduct visual inspection to determine the faulty component that requires repair or replacement. For more information, please contact us at sales@aetech.com.
So I hope you might have seen that a very big transformer, but that is not even ultra high voltage. It is just extra high voltage transformer. Then you can imagine the size of ultra high voltage transformers. So for such a big transformers, they are using the acoustic sensors, and the technology is completely developed. Okay, so from the acoustic sensors, it will be connected to the detector, and then it will be interfaced with the PC, and you can easily monitor what is happening inside the transformer, and they are collecting different signals, and then it is not just a one sensor. Okay, multiple sensors are used to locate the fault based on the time domain reflectometry principle. I hope you know what is time domain reflectometry principle. That is, each signal will travel in a medium, and then therefore during the travel it will be attenuated and also it will be distorted. Okay, any signal which is before reaching the sensor, it will be attenuated and it will be distorted, and therefore based on the time taken for different signals to reach the sensor point, based on that they will find out where is the fault. They will easily find out, locate the fault. Okay, so that type of technology is used in acoustic sensors, and that's what they have shown in that video. Okay, how we have to measure acoustic sensors. So another type of sensor is a transient earth voltage sensor. So this is actually it's like a capacitive probe. Okay, it is used to detect the high frequency PD pulses. This is also mainly used for all high voltage switchgears and transformers and cables. Okay, so the picture also shows 2 different models of TEV sensors. This also operates in a very high frequency. So you can see the technical specification of TEV sensors, and its bandwidth is around 40 megahertz to 80 megahertz, and it's also a BNC connector, and it can easily locate the amplitude of transient earth voltage what is occurring in any equipment. Okay, so just if you connect this sensor to the metal casing of the high voltage equipment, then you can easily find out any signal or leakage current what is happening inside that. Okay, this is the TEV sensor bandwidth. So as I already told, all these sensors what we are discussing today are all working on high frequencies. Okay, so I will also share a small video of TEV.
Welcome to the EA Technology Partial Discharge podcast. Over the next few minutes, we'll give you an overview of partial discharge and its significance in power asset management, and tell you about how EA Technology has developed world-leading know-how and instruments to detect and monitor partial discharge to help you manage your power asset network efficiently and effectively. Partial discharge, or PD for short, can be found in all types of high voltage assets, from switchgear to transformers, and from overhead lines to underground cables. It causes degradation of assets and can lead to failures. A partial discharge is an electrical discharge or spark that bridges a small portion of the insulation between two conducting electrodes. We call this PD activity, and it can occur at any point in the insulation system where the electric field strength is greater than the breakdown strength of the insulating material. This can occur in the voids within solid insulation, across the surface of insulating material, within gas bubbles in liquid insulation, or around electrodes in gas, or it can produce corona. Partial discharge is the most reliable indicator of the true condition of insulation within live assets. Therefore, being able to detect, locate, and measure partial discharge on an ongoing basis is critical to managing your assets as efficiently and reliably as possible. Based on our experience of over 40 years working within the electricity industry, EA Technology has developed a world-leading range of instruments to detect, locate, and monitor partial discharge activity. Conduct a first-pass survey to assess if partial discharge activity needs further investigation with our award-winning UltraTev detector, featuring dual sensor technology with both ultrasonic and TEV sensor. It provides an immediate check for critical partial discharge activity. Easy to use with minimal training, it is the perfect instrument for detecting faults at an early stage. Need more detailed data on your partial discharge situation? Then opt for our UltraTev Plus, which will provide the same functionality as the UltraTev detector, but includes the additional benefits of more detailed data on a clear display and complementary components such as the UltraTev dish to expand the receiving range and contact probe for sealed cable boxes. Locate the exact site of an internal partial discharge fault with our UltraTev locator. It's an easy-to-use, complete, portable partial discharge investigation system which locates, measures, and records partial discharge activity. With 2 probes and 6 sensor technologies, including both ultrasonic and TEV sensors, it is the most versatile investigation instrument in the world. Give yourself a piece of
So yeah, you might have seen that how they are using the TEV sensor technology for measuring PDs. It's a very compact handheld device. Okay, so you can simply touch on any metallic point or surface, and then you can easily measure what is the PD, what is occurring inside the equipment, it's a transformer or any equipment. You can any switch gears or panels. You can easily monitor PD through these handheld devices. Such a level of technological development are happening in sensor technology. So the final one is the ultra high frequency sensor. So as you know, the ultra high frequency means it's operating at 300 megahertz to 1500 megahertz. So it's also an ideal system. As I already told, when we are dealing with PD sensors of in kilohertz or in small megahertz means, then naturally we will be coming across these radio frequency signals and some electromagnetic interferences. So in order to avoid those things, nowadays the technology has gone to ultra high frequency level, whereas 300 megahertz to 1500 megahertz. It means we won't find such a disturbances. Okay, so that's why these type of sensors are developed, and you can see the pictures. So these are all some of the typical pictures of ultra high frequency sensors. As I already told, they have a very high immunity to external electromagnetic interference and also with a very high signal to noise ratio. So this is a very basic block diagram which represents when the ultra high frequency antenna is there and it captures the PD signal and it is converted to electrical signal, and then it is filtered and denoised and amplified, and then it is given to data processing system. So this is a very conventional flow. So these UHF sensors are also used in all applications. In recent times, mostly these UHF sensors are preferred in gas insulated systems and cables and in transformers. Everywhere people are using UHF sensors. And these are all some of the commercial UHF sensors available and at different frequency ranges, and for what application they are using it for. Whether it's for transformers or cable terminations or joints or for generators or any high voltage switchgears, for each and every high voltage equipment, there's a separate sensor UHF sensor technology is available. So we can select based on our requirement. As I already told, the bandwidth of the UHF sensor is almost in the range of 500 megahertz, so ultra high frequency. So this is simply connecting UHF sensors in underground cable. So when we connect it and how they are measuring using UHF calibrator. So I have a small video of UHF sensor also. I will show you that one. So this is the UHF sensor, which is installed on the metallic tank. So inside you can see the windings. Okay. The high voltage windings.
Right, the oscilloscope is now ready and connected to the 4 UHF sensors, and the PC is ready to log the data from the partial discharge once it becomes active. To simulate a partial discharge in this tank, we're just using a small spark plug here which will generate a spark every 2 seconds. And I'm going to go and place that in a certain position in the tank, and we'll see how accurately the software can locate it. For the first test, I'm going to put the spark plug here in the center winding, halfway up, just about level with the outer surface of the winding there. The data is being logged now. In the background, we have the model of the tank showing the sensor positions S1, S2, S4, S3 is down the back there and not visible in this view. Go back to the logging, stop the logging process. Then I'll load some signals that we've accumulated over this period. The software now calculates the arrival times of those for every single pulse and accumulates them into a data file, which we now analyze as a 3-dimensional plot on the timeline, where each of the axes relates to a time difference between a pair of sensors. Now we can define certain clustering tolerance to pick out where the real bunches of data are within this data. And we can see here is one where there are 56 points accumulated in that part of the data set, whereas there are only 11 in this part of the data set. So we select this one, all those arrival times get averaged to give us the best time of flight, and then if we click locate PD, It feeds those drivers climbs through into the system here, and you can see that the cluster, which is based on a tolerance of 0.5 nanoseconds, is right in the center of the middle winding where the spark is indeed located.
So that's what I have told, no, that even in a big size transformer, so they are creating the artificial fault in one particular phase of the winding, and they are able to exactly locate in the three-dimensional view where is the fault. So using these UHF sensors. So in such a way, the technology is developed now. So you can even in a big size transformers or any equipment, you can easily monitor or locate where is the fault. So that is the biggest advantage of these acoustic sensors and these UHF sensors. So far we have dealt with these current sensors, whereas for measuring the voltages, there are also high voltage probes are available. So, but the high voltage probes, the maximum voltage limit is up to 40 kilovolt, whereas in the case of AC, we can up to 128 kilovolt RMS we can measure. So these are all the different types of voltage sensors available, and mostly the 1000:1 ratio is adopted, and we can measure AC, DC or peak voltages through this type of high voltage probes. So the basic voltage principle is simple voltage divider circuit. As I already told, it's a simple R network or C network or RC network. So using those, we can easily measure this high voltages. Okay. So the key points to remember in the design of high voltage sensors are, since these sensors are located for outdoor applications, then naturally we need to have a hermetically sealed construction, and it should have a high seismic withstand design, and whatever we are measuring, the accuracy and the reliability should be good, and at the same time it should be in a position to find out where is the origin of the disturbance or the fault occurring, and it should operate over a large frequency range and excellent transient characteristics. It should measure the very short duration pulses what is occurring in the inside that equipment. And most of the time, since we are going for inductive type of measurement, this core should not saturate, and also it should not lead into ferroresonance problems. So therefore, we need to design the core in such a way that it should not get saturated, and it should not be affected by any discharge or short circuit in the line. Okay, so these are all the important points to be we should remember during the design of high voltage sensors. So if you take a transformer, we have discussed so many sensors. One is HFCT based sensors, and another one is capacitive type sensors, and then ultra high frequency sensors, and then acoustic sensors. So what are all the various possible connections? In capacitive sensors are connected in bushings, and then HFCT sensors are connected in ground, and then acoustic sensors are connected in metallic tank. So like that, in a transformer there are so many sensors located, and people are trying to monitor continuously the operation of the sensors, and is there any fault is occurring in the transformer. And in the cable also you can see in the ground lead we can connect HFCT sensors, and in the joints we can connect TEV sensors, and even in the joints also in the ground lead we can connect again HFCT sensors, and we can also use in the bushings and also in the metallic seats we can use ultra high frequency sensors. So this is for cables. So in any gas insulated switch gears, we can connect like the acoustic emission sensors and ultra high frequency sensors and HFCT and TEV. So all these sensors can be applied simultaneously in any high voltage system, and then we can easily monitor the progress of this type of costly equipments. Okay. So I hope so to some extent I have discussed or I have given some awareness about the latest high voltage sensors and its technology within this short period of time. If you have any doubts, you can always ask. And my suggestion is that this area, this high voltage technology area, is really a very good area where people can work and do a lot of research, and at the same time students who got trained in such testing systems and such measurement systems, and it is just we have discussed today only about the sensors and what are all the sensors, but from the sensors how the signals will come and how the software will work and what are all the softwares to be developed for measuring and what are all the then once we are collecting large number of data, how to classify those data, and then what are all the algorithms or AI techniques to be used for monitoring the data and filtering the data and then clustering the data. There are so many further applications are there, and therefore if a student or scholar who is well versed in both low voltage electronic side and signal processing, and also in knowing some fundamental knowledge about high voltage systems, then they have very good opportunity in very big companies. As I already mentioned, there are so many big giants are there in the world, and they are operating in high voltage systems, and with very good salary the students can get a placement. Okay. So I thank the organizers and particularly Dr. Balakrishnan sir and also the management of Gnanamani College of Technology for providing me an opportunity to share my views on high voltage sensors. Thank you, sir. Thank you.
Thank you very much, sir. Participants,
Yes.
if you have any queries, you can